Hello, guys. Good evening to you all. So, welcome to Data Valley. So, we are the fastest growing edtech company of 2025, and myself, Franklin, and I have almost 3+ years of experience as a data engineer. Thank you all for the amazing response we have got till this point, and I wish you all good luck while you learn. And I encourage you to keep on learning. You know, interviews, recruitment is a tiring process, right? But do not worry, put your all efforts, okay? Be focused and put all your efforts. You will get there someday, okay? And when you get there, I'll be very happy for you all because you are part of this Data Valley community, and I wish you all the blessings from God, okay? And today we are starting our ninth part of our data engineering series. The series has been going amazing, so thank you all for that. And today, let's jump to our video now. Okay, so you all know the routine. Grab your notebooks if you have the practice of taking notes, and grab a cup of coffee as well, so that you feel refreshed, you stay focused, and you feel good about learning because you all would be back from your school, college, or you might be a working professional. So, grab a coffee, just chill, come here, stay focused for an hour. If you like this video, do drop a like. If you have any questions, put your questions in the comment section. I'll make sure that I'll either answer it in this session or if not in the future videos when I go through them. Okay. So, unlike our other series, I think from data engineering part 7, we have been focusing on one subject per day, right? So, today we are focusing on Amazon Redshift. So, Redshift is going to be our key concept today. So, Redshift is part of your AWS cloud, okay, the Amazon Web Services cloud. So, that doesn't mean that, let's say you're a different user, okay, let's say you're from a different cloud. That doesn't mean that you can skip this because having an hybrid cloud knowledge will benefit you at a long run, okay? So even you might be trying to switch your career from one of the cloud to the other one. In that case, you can make sure or make use of this video as well. So I wish you all, I recommend you to learn this as well because we are diving deep, so deep that it makes the concepts very clear. So just 1 hour spent for your own knowledge. All right, now to our video. What is Amazon Redshift and what is its primary purpose? So, Amazon Redshift is a fully managed cloud based data warehouse service offered by Amazon Web Services. So, the key point here is it's a fully managed cloud based data warehouse. Okay, what do I mean by fully managed? With a Redshift, you don't have to maintain any infrastructure or you don't have to provision any kind of application to make sure that your warehouse runs, but rather the Redshift is completely managed by your cloud provider, that is Amazon Web Services. So it is completely managed by them, the infrastructure, the application. All you got to do is you got to request the number of clusters that you need for your warehouse. You can start loading your data and then you can process and then you can perform your analysis just like that. So it is a completely managed cloud-based data warehouse. And talking about cloud-based data warehouse, this is proprietary to your AWS. Okay, because this is a proprietary one to AWS, you cannot have a local system installed in your company. Okay, so this is just going to be in your cloud, and there is no way that you can have your local installation. So it's a cloud-based data warehouse, and this is proprietary to your Amazon Web Services. The primary purpose of an Amazon Redshift is to enable organizations to store, analyze large amount of structured and semi-structured data, typically for business intelligence, reporting, and analytical purposes. So, what is the benefits of Redshift? If you ask me, the key point is you can store your data, you can perform analysis of that data. It might be a semi-structured or a structured data, it doesn't matter, but you'll be able to analyze and you will be able to create some reports, or you will be able to perform further analysis or for your ad hoc analysis. So this is the key purpose or benefit of using Amazon Redshift. Redshift is designed to handle complex queries and scale from gigabytes to petabytes and even exabytes with features like Redshift Spectrum. I'll explain you what this Redshift Spectrum means. So but before that, it can handle complex queries and scale from gigabytes to petabytes and even exabytes. So you're going to have your warehouse and you're going to store your data, and while storing the data, your data can scale. Okay, it can scale as much as possible. The size can extend from gigabyte to petabyte. And talking about Redshift Spectrum, it's a tool within a Redshift where you use Redshift Spectrum to analyze data from your S3 cloud. Okay, S3 storage, sorry, not cloud. So whatever the data that you have in your S3. So what is S3? It's a simple storage service offered by AWS. So whatever data you have in your S3, instead of loading them into a data warehouse, you can use Redshift Spectrum to query and analyze your data straight away. So there is, you're skipping the loading part, but meanwhile you're able to generate reports and you're able to query and perform some complex uh, operations. And what are the features of Amazon Redshift? The first very feature is data warehousing. So data, as I said earlier, it's a cloud-based and managed data warehouse. So data warehousing concept is the core for the Redshift service. The Redshift acts as a central repository for structured and semi-structured data, allowing businesses to consolidate information from various sources for comprehensive analysis. So depending on your business use case, you might try to get your data from different sources, and these data can be of structured or semi-structured, and you load the data and then you can perform your analysis. So data warehousing feature is the primary purpose of your Redshift. Then the scalability. It is designed to handle massive data sets, scaling from gigabytes to petabytes and even exabytes when leveraging features like Redshift Spectrum. So whatever the data that you have, okay, generally a company might have like 1 terabyte, a few gigabytes, depending on the company size. Okay, so even if we have petabytes of data, or let's say worst case you're having even exabytes, okay, it's like a few times multiplied for each petabytes. Okay, so even that kind of quantity can be analyzed by using Redshift Spectrum. So all you do is you load your data into your simple storage service. Instead of loading your data from your S3 to Redshift, that is warehouse, you just use your Redshift Spectrum and start analyzing your data straight away. And then it provides you with analytical performance. So Redshift is optimized for fast query performance, enabling users to run complex analytical queries and generate insights from large datasets. So Redshift by default is optimized for your faster query performance. By providing a fast query performance, it helps you with your analytical performance. As you all know, Redshift is cloud-based because it is proprietary to your AWS cloud, and you cannot have local installation. And because it is cloud based, it offers certain features like scalability, cost effectiveness, and ease of manage compared to your traditional on-premises data warehouses. So scalability, if you need to increase the number of cluster size, yes, you can scale it just like that in your AWS cloud. If you want to scale down, yes, you can do that. And talking about cost effectiveness, it is far better. All you gotta do is spend your operational expense rather than your capital expense. So capital expense would include something like, getting the storage, installing the data warehouse on your premise. So that is not a cost-effective approach, right? But Redshift provides you with a cost-effectiveness approach. It provides you with ease of management because the infrastructure, the application, everything is taken care by AWS Cloud. So as a user, you don't have to fix anything. You don't have to make sure that the physical infrastructure is safe, or you don't have to worry about providing or making sure that security patches are done. You don't have to worry about anything. It is just managed by AWS Cloud. And then business intelligence and reporting. Redshift can integrate with various BI tools and reporting platforms, allowing users to visualize and analyze data for decision making. So even if you have to use native AWS tools, you can use it. For example, you have QuickSight. So AWS QuickSight can be used to generate, or it is, you can get an insight using your QuickSight. But let's say you don't want to use any kind of AWS native clouds. Do not worry. You can connect with various business intelligence tools and reporting platforms, and then you can run your visualizations, or you can start analyzing your data as per your requirement. Redshift offers you a cost effective approach. The reason is it follows a pay as you go pricing model. What do I mean by pay as you go pricing model? So let's say you're purchasing a SIM. You have two options. Either it can be prepaid or a postpaid option. What is a prepaid? So you pay the fees in advance and then you start using the service. And what about the postpaid? So you use the service and based on your usage, you pay your price, isn't it? So similarly, Redshift offers you a postpaid option, or in other words, it's a pay-as-you-go pricing model. So whatever the service that you're using, so depending on that usage, you pay only those pricing rate. So you don't have any upfront cost, or you don't have to pay any advanced fees so that you can use the service. No, you use and then pay for what you have used. No hidden costs. So it allows users to pay only for the resources we consume, making it cost-effective solution for data warehousing needs. All right. Then we have data integration. So Redshift can seamlessly integrate with other AWS services. So you have different AWS services, right? For instance, as a data engineer, the most prominent tool that you would use is AWS S3. You might use AWS Lake Formation. You might use Amazon Kinesis Data Firehose. So to connect with all these, Redshift has a native data integration. So therefore, you can integrate with all these tools, and then you can perform your data ingestion and processing. And it is a very efficient approach as well. This is one of the key factors that I'm going to list now, that is the SQL compatibility. So SQL developers, you don't have to worry about, you might be wondering how can I use the Redshift to generate report? How can I try to use it for generating some analysis? Don't have to worry about it. So like, how do you use SQL with other database? You can follow your SQL standards. By using SQL standards, you are making sure that your traditional form of approach can be availed in your data warehouse. So therefore, it is very user friendly. I would say, in other words, the developer friendly, because all you got to know is SQL, And then by using SQL, you can access all the data and query and perform any kind of analysis using your Redshift. So this is all about Redshift and its primary purpose along with its features. Explain the key difference between Amazon RDS and Amazon Redshift. So RDS and Redshift, they both are completely different to each other. First thing, so how are they different? We will talk about it, but let me give you a small idea, okay? RDS stands for Relational Database Service, okay? So you are going to get a database, okay? The key point here is RDS provides you with a database, whereas Redshift is a data warehousing service. So database is completely different to data warehousing. With database, what would you do? You do a lot of writes, which is a transaction, right? You do a lot of write transactions. But if you consider Amazon Redshift, you're going to have a lot of read operation. So lesser, lesser write, but lot of reads in your Amazon Redshift. So we'll talk about RDS. So the main purpose of using an RDS is it's a managed relational database service that simplifies the setup, operation, and scaling of your relational databases in the cloud. The architecture, talking about the architecture, it supports various traditional relational database engines like MySQL, PostgreSQL, Oracle, SQL Server, and Amazon Aurora. So these are different kinds of database, right? So you have MySQL, PostgreSQL, Oracle, SQL Server, Aurora. So these different kinds of database can be used from your RDS. Okay, that is your AWS RDS. And Aurora is a native database from AWS itself. So it has its own benefits, but we will talk about that in a different chapter. How Amazon Aurora is different to all other, databases like MySQL, PostgreSQL, Oracle, SQL Server. Talking about the use case, I've already mentioned it is a database. So the main thing about the database is it is suited for online transaction processing applications. So it is OLTP supportive. Okay. So what happens with your OLTP? The transactions are handled. So what do I mean by transactions? You're going to have a lot of write functionalities. So where do you use the OLTP? You use OLTP in e-commerce platforms, and you can use an OLT application for content management systems. And depending on the use case, okay, where you are having large number of transaction rates and where you expect your data to have its own integrity, you can go for RDS, okay, because talking about high transaction rates and data integrity, that is the key point for any database, right? So if you're using a database, you would expect it to handle high transaction rate and data integrity as well. So RDS, that is relational database service from AWS, will support all these kind of use cases. And talking about the scalability, RDS has two kinds of scaling. One is vertical scaling and one is horizontal scaling. So for vertical scaling, if I have to explain in a very understandable fashion, let's say I have my own laptop. Okay, the laptop needs to be upgraded. So there are two fixes. Okay, uh, either I can change the what I can say. Let's talk about the memory. Okay, let's not dive anything more because it will be confusing then. Let's say I want to fix the memory speed of my. I need to fix the RAM processor of my laptop. So what can I do? Let's say I have 8 GB RAM. Now what I can do is I can take the 8 GB RAM, I can replace it with the 16 GB RAM. So what it does, it is going to increase the speed of my laptop, right? So I have done a vertical scaling where I'm having the same system, but I've just upgraded its specification, right? But let's say in horizontal scaling, what you do is, let's say I already have a laptop with 8 GB RAM. Now what I can do is I can get another laptop. So instead of, you know, I know it's a very bad example, but what I'm trying to tell is you'll have two laptops now. Okay, let's say let them be even 8 GB RAM, but you're having two laptops, and these laptops will help you with your concurrency as well. They help you with your parallelism as well. But consider that though I might have two different laptops, they have a centralized brain. Okay, so the performance that I do in one of the laptop, somehow gets aggregated. Somehow the operations come together. Okay, so explaining in context to audience, you upgrade the instant type. Okay, you upgrade your database type. So that is what I mean by instance type. So let's say I want to increase the storage. Yes, you can upgrade your storage. Let's say you want to increase the database, uh, the processor itself. Then you can upgrade the processor. But in horizontal scaling, you can scale your RDS using read replicas. Read replicas are nothing but it's like a and secondary database. Okay, let's say you have few databases. You create a replica. Okay, that is what you call as a read replica, and then you have storage limit, but you can have up to terabytes. Okay, in Redshift you can scale up to petabytes and even exabytes, right? If you remember. So talking about scaling, both horizontal and vertical scaling is supported by RDS. And then we have got Redshift. So Amazon Redshift, as you all know, it is a data warehouse as a service. So the purpose of using Redshift is it provides you with a fully managed petabyte scale data warehouse service optimized for analytical processing and large scale data analysis. So it is completely managed by your AWS as your ODS. But the key difference here is you can handle up to petabyte scale. Okay. And the next thing is it is for your data warehouse service, not a database service. And RDS supports transactional operation, and Redshift supports your analytical processing. And then talking about the architecture, Redshift supports a massive parallel processing architecture. What do I mean by massively parallel architecture? Just give me a minute. Okay. So you're processing, but all your data is parallelly split. Okay. So in a different compute node or in a concurrent system, you're going to process all your data. So that is what I mean by massively parallel processing architecture. So all your processing happens parallelly across different nodes, and it supports a columnar storage. Therefore, it provides you with a highly efficient analytical queries involving aggregations and complex joins across larger data sets. So, database supports you with transactional, and warehouse supports you with analytical use case. And as you can see here, it utilizes massively parallel processing architecture. And then, okay, the use case. It is ideal for businesses that completely depends on business intelligence, reporting, operational analytics, data warehousing, where query performance on vast amounts of data is critical. So if you are having a data warehouse use case, go for Redshift. If you have only something to do like reporting, go for Redshift. If you want to perform some kind of analytics, go for your Redshift. But rather, if you have a lot of large operations, large write operations, go for RDS. If you have a lot of write operations happening, then go for your RDS. And talking about scalability, Redshift offers with horizontal scalability, And how does it support horizontal scalability? It supports horizontal scalability by adding more nodes to your cluster. So you have different compute nodes within your Redshift, okay? And you can expand or you can add more nodes to your cluster, allowing for your petabytes of data storage and high concurrency analytical workloads. So Redshift doesn't support vertical scaling, all right? It's more about horizontal scaling. Describe the architecture of an Amazon Redshift cluster, including leader nodes and compute nodes. This is a very important chapter or question, I would say. Please, put all your attention, okay? Before I explain all the components and how they interact together, first let me explain you the diagram, okay? So once you get the picture in your brain, then it'll be better for you to understand the theory. So you have your client application, all right? From your client application, you connect to your leader node. So we will talk about the leader node, but just know that your client application interacts with your leader node. How do they get connected? They use either JDBC or ODBC connection. So your client application connects to leader node with JDBC or ODBC driver, and then this leader node further assigns or request for more compute nodes. So compute nodes are like a slave. It's more like a master slave architecture, okay? So leader node is your master and compute node is your worker node. So the leader node connects with your compute node, and within compute node you have node slices, okay? And the leader node and compute node together forms your data warehouse cluster. Now let's talk about each of the components so that you get a clear idea of what these components do individually. So as you have seen earlier, Amazon Redshift cluster is designed for massively parallel processing and consists of two primary types of nodes, a leader node and one or more compute node. So Redshift, as we already know, it has a massively parallel processing architecture, right? And now within this architecture, it has two primary types of nodes. One is the leader node and the other one is a compute node. Talking about the leader node acts as a central coordinator for the entire cluster. So you can consider a central coordinator like a central CPU or a central brain, which is going to handle all your responsibilities of your Redshift cluster. Okay. Now, here are a few of its responsibilities. First, we have got client interaction. So, what do or how do we do a client interaction? So, you have your client application, and all the communication are handled from your leader node using JDBC or ODBC driver. Then you have got query processing. So, query processing, in talking about query processing, it passes and optimizes SQL queries. So whatever you're sending all your, uh, you're communicating with your leader node via an ODBC or a JDBC driver, right? So all these communications are happening using your JDBC and ODBC driver. That is very clear. And now all these SQL queries or the question, the syntax that is being passed through, the parsing of those SQL queries happen in your leader node. And it not just passes it, it also optimizes your SQL query. So therefore, it develops an execution plan to be distributed among the compute nodes. So whatever the SQL query that you provide to your leader node, it passes to it, okay, and then it optimizes it. And once the SQL query is optimized, then it is created into an execution plan, and that execution plan is distributed to different compute nodes. I hope that is very clear. And then first it interacts with your client, then it can process your query, and now the workload distribution. So whatever the execution plan that you have created in your query processing layer, then you distribute the portion of your query execution plan and the corresponding data to the compute node for parallel processing. So you will have a plan, right? So this plan is sent to different compute nodes, and not just the execution plan but also the data as well. So the data is sent to different compute nodes, and then the compute nodes does the processing. What happens after processing? So when the processing is done, the leader node again receives the results from your compute node, aggregates them, and then returns the final result to your client application. So what's happening? The client sends the SQL query. The leader node optimizes your SQL query and it generates a execution plan. And now what it does, it sends the data along with the required execution plan, and the results or the intermediate results that comes from your compute node are aggregated again in your leader node, and the final output is again sent to your client application. And it also provides you with metadata management. So what happens is it manages your system metadata and coordinates data distribution across the compute node. So whatever the data that is getting processed, it gets distributed across your compute node. And whenever the data is getting, distributed across the nodes, the leader node keeps a track of it. So it keeps the metadata of what data has been distributed across the compute node. And then we have compute nodes, okay, the node next to your leader node, or in general terms you can call it as a worker node. These nodes are responsible for storing data and executing query operations in parallel. So the leader node sends all the query along the plan and the data, right? And now the compute node is responsible for storing all this kind of data and executing the query operations. So what are the key characteristics of your compute node? So the key characteristics are, it helps you with the data storage and processing. So each compute node stores a portion of the cluster's data and performs the actual data processing tasks as instructed by the leader node. So the execution plan, it is sent to your compute node. Okay. And now these cluster nodes or your compute node performs the processing on your data. And then you have a concept called node slices. So these node slices are, so when the compute node, you have your compute node, right? Each of the compute node is divided internally into multiple slices. Okay. So you have your compute node. Okay, leader node communicates with your compute node. And within compute node, you have node slices. So what are these node slices? The node slices are logical partitions of your CPU, memory, and disk space. So these are logical partitions. And what these logical partitions will enable you to do is, they help you to process your data in parallel. So as said in here, these slices work in parallel to process a portion of the workload assigned to the node. So the compute nodes along with the node slices, it helps you with the parallel processing. And then you have got parallel execution. So queries are executed in parallel across the slices within a compute node and across multiple compute nodes, leveraging the MPP architecture for high performance. So as you have seen earlier, the leader node partitions the data and the execution plan and sends it to a cluster of compute node. So what is a achievement here? The achievement here is that your data has been already split across, your plan has been split across, and now your processing is split across as well. Therefore, it supports parallelism, concurrency, and enabling high performance. And talking about scaling, the compute capacity of a Redshift cluster can be scaled by adding more compute nodes or upgrading to more powerful node types. So what you can do is, whatever the nodes that you're using, either you can upgrade the specification or you can add more cluster nodes to enable scaling out. Okay. In short, the leader node orchestrates the overall query execution because it's your master node, right? It orchestrates your overall query execution, while the compute node performs the heavy lifting of data storage and parallel processing, enabling Redshift to handle large scale analytical workloads efficiently. So, here I've got the official diagram from the AWS. So as you see here, I mean, forget all these because it includes multiple architecture. But for now, let's talk about Amazon Redshift, the provisioned one. Okay. So you have your clients here. Your client is interacting with your JDBC or your ODBC driver. The ODBC and JDBC connectors connect with your leader node. And within your leader node, you have your compute nodes. And within the compute node, as you see here, the blue ones are your node slices. So your SQL query or the optimized execution plan is sent to different compute nodes along with the data. And once the data is processed, it again sends to your leader node. Okay, even if it is intermediary or the final result, it doesn't matter. So it is sent to your leader node, it gets processed here or aggregated here, and then the final result is sent again to your client application. So this is how your Redshift components work together to enable a high performance. And then what are distribution styles in Redshift and how do they impact query performance? Name and explain the different types. So talking about the distribution style, okay, we already discussed that you have something like execution plan and your data gets sent to different compute nodes. And now that is where your distribution style comes into play. So whatever the data you have, how do you send it across the compute nodes of your cluster? So you gotta determine what kind of style are you following so that the data rows are distributed to your multiple compute nodes. The choice significantly impacts query performance, especially for join operations and aggregations, by minimizing data movements between nodes. Let's talk about the different types of distribution style. First thing what you have is auto. If you don't specify your distribution style, the Redshift automatically opts for your auto mode or it's the default mode. So what happens in the auto mode is that there are three kind of distribution style called the key, the even, or the all. So you have three kinds of distribution style, and these distribution style, okay, only in the auto mode I mean. So these distribution style are determined based on your table size and how you are planning to use the query. Okay, so you have your table size, and then on top of your table size, also your query is taken into your query is also taken into consideration. So depending on the table and your query, your Redshift can automatically choose which kind of distribution style would the system wanted to have. And this is the default setting if you don't specify any distribution style. So unless you don't specify, or in other words, if you don't specify what kind of distribution style do you prefer, then Redshift automatically can choose the best distribution style. All right, and gotta remember this: the distribution style is explicitly specified during the table creation. Okay, it's not something that you do later, but rather the moment you create a table, make sure that you specify your distribution style. And now we will talk about the three different styles, okay? The key, the even, and the all distribution style. Because if you don't specify any of this, then the auto comes into play. But there are chances where you can specify if you prefer even style, the key style, or the all style. Talking about the even style, rows are distributed evenly across slices in a round robin fashion. No specific column is used for distribution. This style is suitable for tables that are frequently joined or when no clear distribution key exists. While it ensures even data distribution, it can lead to significant data redistribution during joins if the join tables are not distributed on the same key. So, what I'm trying to tell is if you use the even strategy, all your rows are split across in an even fashion. Okay, so you have node slices, you have your data. So the rows are distributed evenly, okay, across your each node slice, and you don't specify any column. Okay, there is no choice for you to choose a specific column. Why is that? Because you have specified that you want the data to be evenly distributed across the node slice. So your column name doesn't make any sense in this context. And then this kind of style is suitable when you're not okay, this style is specifically useful when you're trying to not perform a join operation. So whenever you have a table of tables that you don't perform a frequent join function, join operation, and when you don't have a clear distribution key. So what do I mean by distribution key? So let's say when you choose a column, you will be having some distinct values, right? So if you don't have any kind of such important distribution key within a column, then you can opt for even distribution style. And then we have key distribution style. So what happens in the key distribution style is that your rows are distributed across your node slice depending on the value in a specific column. So you got to specify your column, okay? And depending on each row or rows with some distinct key or a different key within the column, that is how the key distribution style works. So you specify the column and depending on the distinct keys within that, okay, in other words you can call it as dist key or distinct key. So depending on the dist key, your data is split across your node slices. So all rows with the same kind of dist key values are stored on the same node slice. If you have a same type of key, that is stored in the same node slice. So it makes sense, right? For example, let's say I have a column. It has only 4 distinct keys. So if I had to split it, so one key gets a particular node slice and all the data for the particular disk key gets settled in that, right? So depending on your disk key of your particular column, your distribution happens. This is highly beneficial for join performance when joining tables on their respective dist keys. So if you're trying to perform a join operation, okay, and when you perform a join operation, and when you have tables and you're performing join on them, if they have a respective or the same disk key, then it is very beneficial for your join performance. And why is that? Because the key distribution style helps you to co-locate your matching rows, therefore minimizing your data transfer between the nodes. Choosing a dist key that is frequently used in a join predicates and has high cardinality is crucial for your optimal performance. So the dist key that you choose, that is very important because that is the one that you primarily use for your join predicates, and make sure that you have high cardinality. Why is that? Because let's say you have a 10 cluster. Okay, you have a 10 node cluster, or you have, let's say you have multiple node slices, and you have a data, and let's say it has only four different dist keys within a column. In that case, you're having 10 nodes, but your data gets split across four different nodes, which makes that which makes the other six nodes very inefficient. How come they are inefficient? Because you're not using them, and when you don't use it, you're you know hindering your performance, or you're not utilizing your resources properly. Therefore, make sure that your data has high cardinality, which will enable you to use your distribution style, a very efficient one. And then you have got all. So talking about the all distribution style, what happens is that you create a copy of your entire table to each of the compute node. So you have your table, let's say a small table. Okay, this is primarily useful for small table anyways. So you have your small table, and the copy of this small table is distributed to every compute node. This style is ideal for small dimension or lookup table. So if you have a smaller table, okay, or if you, let's say you have just a lookup table, then this is okay, because your copy, okay, or your table is getting distributed, right? And if it is a large size if it's a large size table, it is going to impact your performance. It is going to cost you some storage, right? So make sure that the table that you send is small dimensional, therefore it doesn't take a lot of storage. While it eliminates data redistribution for joins involving the all distributed table, it consumes more storage and can be inefficient for large tables due to data replication. So even if you have your even if your table is small, if I'm sending it to 10 compute nodes, it is going to cost me some storage, right? So make sure that your table is a small dimensional one. Therefore it doesn't, you must always have efficiency more than inefficiency. So just because I'm sending all the small table to multiple nodes, it is okay, I'm trying to gain some performance, but if I'm losing money in the storage, then it is not worth it, right? So you need to find the balance between the performance and the cost effectiveness. And now let's see, how does it impact the query performance, your distribution style. So first thing, it minimizes the data movement. The primary impact of distribution style is that you can minimize data movement during query execution. So if the data is actually located in the different node, okay, let's say you're using key distribution style, and your data is now split across, and now as it is distributed, you can easily locate your data, right? Because all your particular key data is going to be stored within a node slice. So therefore, instead of reshuffling your data, or instead of you know impacting your performance, because you're just taking only the data that is required, you're gaining a performance. So Redshift can perform joins and aggregations locally without needing to redistribute data across the network, which significantly improves performance. Because let's say you are using a key style, your data is split across, right? When you split your data across different nodes, you get to know what is in the particular location. So depending on that location, you're enabling a predicate pushdown. Then you have your parallel processing. So effective distribution ensures that data is evenly spread. Because you have multiple compute nodes, when you distribute the data, it is spread across, right? So when it is spread across, it is going to support parallel processing. And let's say you have an uneven distribution, okay? An even distribution is beneficial, but let's say you have an uneven distribution. What are the scenarios you might have an uneven distribution? Let's say I have 100 columns, sorry, let's say I have 100 rows having the same dist key and a million rows for a different dist key. And when I try to perform distribution based on the key, one node is going to have 100 rows and the other one is going to have a million. So even see, let's say million is a extended or exaggerated purpose I'm explaining. But let's say even if it is 1,000 or 10,000 records, but you can see that you have a data skew. So uneven distribution can lead to data skew, where some nodes become bottlenecks, hindering overall query performance. And then talking about storage efficiency, all distribution, while beneficial for small lookup tables, can lead to increased storage consumption due to data replication. So when you use all method, you are sending or distributing a data across the nodes, right? So you are going to consume more storage. So make sure that though you might get some performance gains, you're spending a little money on your storage. And talking about the storage efficiency, even and key distribution style is more efficient. All right. To our final question of the day, what are sort keys in Redshift and why are they important for query optimization? So sort keys in Amazon Redshift define the order in which rows are physically stored within a table on disk. By sorting data according to specific columns, Redshift can efficiently retrieve data, significantly improving query performance. So, what is a distribution style? So, distribution style is how you distribute your data across your different compute nodes, right? And talking about the sort keys, so whatever the data is in different node slices, how do you sort it? That is the main point of your sort key. So you have two types of sort keys. One is the compound sort key, and then you have interleaved sort key. So talking about the sort key, I'm sure that everyone knows what is sorting, right? So sorting can happen, let's say a descending order, ascending order. So we have different types, right? Even sorting can be performed based on a key value. But when sorting, you have two types of sorting within Redshift called the compound sort key and your interleaved sort key. So in compound sort key, the sorting is based on the order of columns specified in the sort key definition. So when you try to sort your uh, data, you try to specify it, right? And you specify the columns. So depending on the business use case, you specify the column. So what happens in the compound sort key is that the order of your columns have a specific importance. So what do I mean by order of your column? So first, the data is sorted by your leading column. So whatever the column name that you specify at the first, it gets the leading priority. And then let's say you're adding one more column to your sort key, which is a compound sort key. So now the second priority is given to your third column, and further on, so it goes on, right? So the more column names that you specify, so is the order in which your sorting happens. So there is always a weightage for your ordering of columns, and this is highly beneficial when queries frequently filter or join on the first few columns of the sort key. Why is that? Because in compound, the order of columns matters, right? The priority is given to your leading column. So if you are going from 1 to 3, the priority is similar. So the first column is given first priority, the second column is given the second priority. That is how your sorting is going to take place. So if you do these kind of compound sort keys, this is beneficial when you are trying to run frequent queries. because as you have already sorted the data, okay, now it is easy for you to perform the join operation, right? Therefore compound sort keys are useful in that scenario. Then you have interleaved sort keys. So what is interleaved sort keys? So these interleaved sort keys will assign equal weights to all the columns in your sort key. So in compound sort key, the ordering of your columns gets a weight. But in interleaved sort key, all your columns within the sort key gets the equal priority or your equal weight, aiming to provide a more balanced sorting across multiple columns. So no matter how many columns that you provide, you are trying to find a balanced sorted approach by using interleaved sort key. This type of interleaved sort key is generally more effective for large tables and when queries filter or join on different or combinations of column within the sort key. So this is more effective when you're using larger tables. All right. So now, what are their importance with your query optimization? Generally, sort keys provide you with a query optimization. Okay. And now let's dive deep. How do they provide us with those kind of benefits? First, you have something called as zone maps or data skipping. So what happens with your zone maps and data skipping is that your Redshift by default maintains something called as zone maps. If you ask me what is zone map, I would say that zone maps or metadata about the minimum and the maximum values within data blocks. So your data is going to be split across, right? Based on the distribution style. And by using sort key or also sorting the data within these data blocks. Now you have the metadata, which is going to specify the minimum and maximum values for each of the data block. So because your data is already sorted, your zone maps or your metadata becomes highly effective where when you're trying to run a query, okay, the Redshift allows you to identify and skip over chunks of data that do not specify query predicates. So let's say I'm using a key distribution style and now my data is sent across different compute nodes. And when I'm trying to query, my Redshift will get to know from the metadata that what is the maximum value, what is the minimum value of this particular data block. Therefore I can easily skip it because I don't have to perform a full table scan unwantedly, because it is going to cost me uh, you know cost as well the storage and the performance. So rather I can skip it based on the metadata management. This drastically reduces the amount of data scanned, leading to faster query execution. So because you're avoiding, full table scan or larger scales of data scanning, you're using a sort key, which will enable the zone map, that is your metadata. And therefore, by using metadata, it enables you to have a faster query execution. Then, the next importance is efficient range queries and filtering. So we have already seen that your metadata is going to store about your maximum and minimum value within a data block. This is same now as well. The difference is in the other one I'll be saying that where this is equal to. But in this I'll be specifying a range, right? Where date between, so I can specify a range of values. So it is same as well. By specifying the range condition, it goes to your zone map. Okay, it checks if the particular value or the range is within the data block, and your zone map will help you to provide you an idea, I mean, to the Redshift about what data it holds or what is the value of those data. And if the data is present, it is going to scan that. If not, you are still avoiding a full table scan, therefore providing you with a better performance. Then you have optimized joins and aggregations. So when tables are sorted on join keys, Redshift can utilize merge join operations, which are highly efficient. Similarly, group by and order by operations on sort keys can be performed more efficiently as the data is already pre-sorted. So let's say you're trying to perform a group by or an order by, and then for these kind of operations, your data is already pre-sorted. Okay, because your data is already pre-sorted, you can efficiently use merge join strategies as well. So merge join strategies, because your data is already sorted, it's going to give you a better performance. And then the next importance is that you will have reduced IO operations, so input output operation. How is that possible? So you are having a metadata. So if you provide a where clause, you're going to only scan those particular data blocks, or you're skipping it. Same for your range as well. And now what happens is that you're going to have only efficient data access by sorting keys minimum the amount of data that needs to be read from the disk. So the level of reading, or you're skipping your full table scan. Therefore, the amount of read functionality happening from your disk, that is, in other words, the amount of input and output transactional operations are reduced because you're not performing full table scan. You're not going through the full data block to attain some result. And by using zone maps, you can increase your performance by reducing the input and output operations. So this is the sort key, and the other one is disk key. So I'll reiterate this. Disk key is how you distribute your data across your compute nodes, and sort key is how you sort your data within a node slice. Okay, so that is the core difference between the sort key and distributed key. So today we learned about sort key, we learned about the disk key. Then we also had a look on the architecture of your Redshift and its components as well. We learned the difference between the RDS and Amazon Redshift. Also, we started today with what is Redshift and what are its primary purpose and features. So that is all for today. I hope this session was very beneficial to you. So from mostly from the next video or after the completion of the